All right. So do you guys have any questions before I get into it again here? Do I have money? I mean, some. Why? Hey, I thought you just got the scholarship thing. Did you already spend it on Twitter stock or something? I mean, like what?
Do you believe that someone can have enough money?
Do I believe that someone could have enough money? I believe that the government already has enough money, yes. So, like, the government's not a people, not a person. It's like, well, okay, fine. I don't know. So you want more money, huh? Okay, I see. So I wanted to try to look at an example or two today on, the argument principle and Rouché's theorem again. So I tried to give you, proof of it last time, and I think I'm close to it, right? So I'm going to look at example 8.25 that I gave you guys, because it's the example in Gamelin on the argument principle. It's a solid example, but it's like a page of text with no picture. Well, the picture's on the next page, and it's so complicated, I'm just like, I don't want to try to lecture that, So this is example 8.25 from, rats. I showed you guys this book the other day. I think it's Matthews and Howell. So here's the example. We have the image of the circle C2. So what's C2 of 0? I believe this is Z in the complex plane, right? Such that the modulus of Z is equal to 2. So it's the circle of radius 2 centered at the origin. I think this is notation here, all right? And then he's going to look at the map f of Z equal to Z squared plus Z, all right? So what did the argument principle say?
Argument principle?
Yeah, I'm trading. Argument principle 2 said what? If we
derivative is equal to 2 pi times the boundaries. Like this is the difference of the boundaries.
Well, I thought it said that the wasn't it the number of
Zeros times the number of singularities?
Yeah.
Minus the number of
minus number of
singularities
singularities
times 2 pi.
times 2 pi.
Z equals 0. And roll over the boundary d arg f of z.
Yeah. So it was. So let's see. We did first of all. We did the.
I'm guessing d is the differential.
We did this right
Yeah.
over f of z on the boundary of d, and then that was basically the integral over the boundary of d of the differential of the argument, because we explained that the integral, the natural log part of the modulus of f of z, that integrates to 0 around the closed curve, right? So what this is, right, this is the net change in, angle for, if you look at it, it's the same as the net change in angle for f of the boundary of d. So you're studying the angle not of the curve directly, right, but the f of z, which is the image of the curve. So what that integral is the net change of the angle for the image of the curve under the map that we're studying, all right? So now, of course, this is a very silly example in terms of the theorem. The example in Gamelin's more impressive because well, first of all, the image curve is way, way more complicated, right? But second of all, you can't just factor the stupid polynomial you're looking at, right? Like, what are the zeros of z squared minus z? Do we need the argument principle for this? Like, certainly we don't, right? You guys can tell me the zeros of z squared minus z plus z, right? What are they?
-1 and 0.
-1 and 0, right? But again, for the purpose of illustrating the argument theorem, let's go through it. So if we look at, so what's the parameterization of C2? So C2 0 has, let's say, gamma of t equals 2 e to the it, 0 less than or equal to t less than or equal to 2 pi. This is a parameterization of the curve, right? And then we can look at the image, f of gamma of t. What do we get? We get 2 e to the it squared, right, plus 2 e to the it. All right? And that gives me what? 4 e to the 2it plus 2 e to the it, which we can write in terms of sines and cosines as 4 cosine 2t plus 2 cosine t plus I times 4 sine t plus 2 sine 2t rather. Plus 2 sine t, yeah? All right. And if we look at the next page, right, here's a picture on page 349. They've got a picture of this curve. It looks like this, yeah? So there's 2. Here it's -4. So it's got a loop that's like this. And then it's got a bigger loop. Oh, I didn't do it very good. Sorry, this is supposed to go all the way out. This is not a very good picture. This is actually all the way out to 6. Okay. Sorry, I'm not doing a very good job. The picture on page 349, it's more like, it looks more like, let's see here. I still haven't done it right. But anyway, the inner loop is smaller. It's not like this, yeah? So when you put t equals to 0, where are you? You're at 6, right? This is t equals to 0. And then to get over to -4, that I believe is t equals to maybe pi over 2? Yeah, well, no, that's not it either. But anyway, as we trace t out, we go like this, and then it crosses through to over here, and then it loops back, and then finally back around. This is t equals 0, and also eventually it loops back at t equals to 2 pi. Now, there are various methods for drawing such pictures, right? Like, how do you graph the image curve? I think, using some kind of computer-aided graphing is a good idea here, GeoGebra or whatever. Let's see, let's just, for the sake of a little bit more commentary here, when we get to t equals pi over 2, where does f of gamma of t at when we're at pi over 2?
Pi over 2.
Yeah.
Zeros for the first terms. So 0.
Well, I don't think I get, but notice that 2 times pi over 2 is pi.
Yeah.
So that's -4. But you agree the cosine is 0. The sine of 2t is also, that's sine of pi.
You get I plus 2I.
Plus 2i. So minus 4. So my picture isn't quite right, is it? So yeah, there's actually kind of like a, it's here-ish. I think that's where there's kind of like a vertical tangent in the image curve, truth be told. So that's where we get when we get to pi over 2. Where are we when we get to pi?
That becomes pi over 2, so that's 0. That becomes pi, that gives you minus 1, so that's minus 2.
So yeah, I think we get 4,
And that gives you
4 minus 2, which is 2.
which is 0, and that gives you pi.
So I believe, yeah, the other ones are 0, right? So I think this point right here is t equals 2 pi if I'm getting it right. So like you start at 0, you go do 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 0 to pi, and if I'm right, this if I did this right, there'd be a point down here which is like minus 4 minus 2i. I'm guessing that's gamma. That's f of gamma of 3 pi over 2. Because f of gamma of 3 pi over 2 would be like cosine 3 pi for the 2t term, which gives us a minus 4. Then the 2 cosine t term is 0. And the sine of 2t term is 0 because it's a sine of 3 pi. But the sine of 3 pi over 2 is minus 1, so we get a minus 2i from that over here like that. So anyway, that's how it happens. Okay, so what's the change in argument then? So you can see the change in argument for this curve, right? Can you understand it intuitively? Right, so we just look at the curve, we start here, and the angle does what? It increases all the way over to here. The angle of the curve has gone 2 pi when we get to there, right? And then another 2 pi like that. So the net change in the angle around the image curve is 4 pi. So we get the number of zeros minus the number of infinities times 2 pi equals to 4 pi from this graphing here, yeah? So yeah, the number of infinities in this case, again, is 0. And so we get n sub 0 equals to 2, which of course is totally unsurprising because we knew that if we look at the curve, right, if we look at C0 of 2, right, in other words, modulus of z equals to 2, right, that there are, the 0 is here at 0, and also, where was it? Minus 1, right? Because f of z is z times z plus 1. So that actually has zeros at 0 and minus 1. So, yeah. So using argument principle number 2 directly to solve problems, it's kind of fun, but Rouché's theorem is a far more, I would say, accessible tool. Like you don't need the ability to sort through these kind of, what's the image of the curve under a map question. Like the image of a curve under a map is generally a sophisticated and somewhat difficult thing to sort through for a given curve in a given map. Rouché's theorem, on the other hand, is just based on like making the right estimate and following it through. So let's look at an example of Rouché's theorem. What was Rouché's theorem? It's not on the handout I gave you guys, right?
Yeah,
It is? Where is that thing then?
349, right under the image you drew.
Oh, I'm a dummy. Thank you.
Suppose you got some space with some singularities.
I can erase you?
Yeah.
Yeah. I got to bring some cleaner, and the board's getting messier and messier as the semester goes on, isn't it? Okay, so Rouché's theorem on page 349 of the handout I gave you. Of course, we stated it in class last time, right? So we stated it again here, theorem. Rouché's theorem. Suppose F and G, oh, wait a minute. Oh. This is a more sophisticated theorem, a more sophisticated version of Rouché's theorem than we stated last time. But I'll state it. Suppose F and G are meromorphic. What's that mean?
Analytic with some zeros, but they're finite.
Yeah. So it means, yeah, analytic at all but a finite number of, well, since D is a bounded domain, there has to be a finite number, okay? Actually, this is a simply connected domain. Ooh. So last time we had bounded domain. So simply connected, I don't think has to be bounded. Yeah? It doesn't have to be bounded. And so since it doesn't have to be bounded, we could have an infinite number of singularities. Because if you don't have a bounded domain, you could spread the singularities out. You don't have to have an accumulation point. So we could have an infinite number of singularities, but each one of those singularities has to be a pole. It can't be an essential singularity for the functions. All right? And we're going to let C be a simple closed contour in D. What's that mean? What does it mean to be a closed contour? What's this mean? ZF minus PF equals ZG minus PG. I mean, I think if you take a look back at your notes from Monday, this looks quite a bit different than the theorem I called Rouché's theorem Monday, doesn't it? Can you tell me so to answer my question, what does simple closed contour mean? So simple, in this context, I believe, just means it doesn't have like a self-intersection in the sense that it's like a loop, all right? It's not like a figure eight. Closed means that it's not open-ended, right? It comes back to where it started. So, so like a simple closed contour would be a loop, not a figure eight, okay? In other words, a simple closed contour is one which we can smoothly deform, continuously deform to a point. All right. Anyway, meromorphic though. See, in Monday, we didn't say meromorphic, we said analytic. We said F and G were analytic and that there were no zeros I don't even know if we said that were there. Did we even say there were no zeros?
Let D be a bounded domain with piecewise smooth boundary.
Mm-hmm.
Let F of Z be analytic on D, union boundary of D. If the, it does say F of Z. Yes.
So G, F, and G? G of Z and F of Z?
Yeah, and if the modulus of G of Z less than F of Z, the modulus of F of Z for Z in the boundary, then F of Z and F of Z plus H of Z have the same number of zeros in D counting multiplicities. Yeah, and then F of Z and F of Z plus H of Z have the
Oh,
same.
wait a minute. Yeah, I was thinking F of Z was equal to what? It was equal to G of Z plus H of Z, is that right? Or the other way around?
Yes, yeah.
And so what was the...
But F of Z has to be greater than G of Z. Yeah, flip-flop on it.
F of Z is greater than
Yeah,
G of Z?
by definition.
So what's this H?
That H is like, so like in the example, when we proved the FTA, F of Z was Zn, and H of Z was An minus 1 Zn minus 1, da 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 da. That's a naught,
So this was Z to the N,
yeah, and that was the rest.
everything else, not leading terms. In our example at the end of class. And this was an arbitrary polynomial,
Yeah.
a monic polynomial. I might have had an a sub n on that, I don't remember, but
No.
I didn't,
Oh,
okay.
No.
Okay.
It was a monic.
Okay, cool. So our Rouché's theorem, as I stated, it assumes f of z is equal to g of z plus h of z, is that right?
Pretty much. The hypothesis implies that f of z is non-zero, and thus f of z plus h of z is non-zero.
Is the so there's no g, right?
Yeah, you didn't write a g in there.
So f of, I just have, I'm getting confused here. Sorry,
This is Galen's definition.
is it Gamelin? Yeah, I think so. What do you have, Jade? Do you have for Rouché's theorem last time? We have f of z and h of z
There you go.
analytic, right? On D union the boundary of D, and D is a what? Yeah, and then if, this is page 229 in Gamelin, if the modulus of h of z is less than the modulus of f of z for z in the boundary, then f of z and f of z plus h of z, right, have same number of zeros in D. So, and B is a bounded domain with simply piecewise piecewise smooth boundary. So D is bounded. So this is also called Rouché's theorem, yeah?
Yeah.
So how can these be the same theorem? I mean, the one in purple at the top, right, from Matthew's book is a more sophisticated version of Rouché's theorem, right? So analytic is a special case of meromorphic, right? So if it's analytic, that means there are no poles. So I'm pretty sure this notation, this is the number of zeros for f is equal to the number of zeros for g, minus the number of poles for f, minus the number of poles for g. And you can pretty much see how this would have arisen from our proof last class, because we really just used the argument principle, number 2, in the case that there were no,
But it says right there
singularities.
that you don't have zeros on C.
That is also true, but that doesn't mean it doesn't have, this, no zero, f is no zeros or poles on C, that we derived in our proof of this one. So that's a necessary, this data is a necessary consequence of this data. But anyway, I'm just saying, I wanted to answer the question what this notation means. I'm pretty sure that this is just the number of zeros for f and the number of zeros for g are equal. Let's see here, I'm trying to bridge the gap here. F and G are meromorphic. What is H as it relates to F and G, do you think? Or does that even make sense as F being used in a different sense here and there?
I think H of G is F of Z plus G of Z. Wait. Well. Yeah, I think essentially H of Z is that first one, and F of Z is the other one. Like just equate the inequalities. Because
I guess this should be G, right? Does that make sense? Let me just throw that out there. Does it make sense to just think of this as being the G in the purple theorem? At least then the conclusion would be the same. The number of zeros for f is the same as the number of zeros for g. There are no poles in the Gamelin version. If that's g of z, right? That means what? H of z is equal to what? G of z minus f of z, right? And that's the condition we're assuming in Gamelin's theorem. And this is greater than what? The absolute value of the modulus of g of z minus the absolute modulus of f of z. Yeah, I don't see it right off. I mean, let me stop this. This is not productive, guys. Sorry. My point to you is we can either try to use this version or that version when we try to solve the problems here. Okay, so I like Gamelin's version more, honestly. It's easier for me to think about. Let me see if I can show you what I mean. So sample 2. So we have f of, well, he calls it g of z, but I'm going to call it, oh fine, I'll call it g of z. G of z equal to z cubed plus 9z plus 27. And we're supposed to show there are no zeros in D2. So this book, I believe D2 of 0 would be z in the complexes such that modulus of z is... See, I'm not sure if it's an open disk or a closed disk, guys. So I'm not. Unfortunately, I should have grabbed that book with me. My bad. I thought, oh, I'll scan it and make a printout. That will solve our problems, and obviously has not. But we are then supposed to show that there are 3 zeros in D4 of 0. Now this is number 4, so we're not going to have any help from the answer key, right? Actually, let me just forget about this for a second and work something a little bit easier. So yeah, my apologies. Let's see here. So example 2, let's suppose we have, g of z equal to, z to the 10th plus 3z to the 9th plus 6z cubed, minus 3z squared plus 2z plus 10. So here's my challenge to you. Find r greater than 0 such that all the zeros of g of z are within, modulus of z less than r. So I recommend we think about Gamelin's version, all right? So what we want, I'll think of this as being my f of z, and I'll think of this as being the perturbation, h of z. It's the perturbation of f of z. See, f of z is nice. How many zeros does f of z have within a,
Maximum 10.
it doesn't have a maximum. So if I'm looking at the circle, of radius r, right? And I'm looking at f of z equals z to the 10th. How many zeros does f of z have inside the circle? Actually, for any r greater than 0. Precisely how many?
For any r greater than 0, 1.
1? But we count multiplicity, right? So in the notation of Matthews, nf oh, I guess ZF. See, I'm sorry, guys. I wish I had my office is working against us. I can't find my notes at the moment. ZF, the number of zeros for F is equal to 10, right? Because we have Z naught equals to 0 is a 0 with multiplicity 10, right? The 0 is 0. It has multiplicity 10. This we can just see, Z to the 10th, right? That's a 0 of order 10. So what do we need to apply Rouché's theorem? To say that the number, we would like to say that the number of zeros for F is equal to the, we'd like to see that the number of zeros for F is equal to the number of zeros for G, right? If what? If we have what? We need the absolute value of h of z is less than the modulus of f of z, right? Now, thankfully, that's not just for z inside the curve, right? It's for z on the curve. Notice that. So this is, we need this estimate for what? We need this for modulus of z equals to r. So what do we need? We need the absolute value of, 3z to the 9th plus 6z cubed minus 3z squared plus 2z plus 10, right? We need that to be less than modulus of z to the 10th. Uh-huh.
Like, are you saying what's the minimum R or just find an R?
Well, sure.
So we're going to find an R.
I mean, I'd like for you to tell me an R that will work. That'd be good. I mean, certainly this is equal to r to the power 10, right? Yeah. And can we, I mean, you could try to literally solve this equals to that, but that seems as hard as the original problem. You're just factoring that thing.
Just pick an R big enough.
What R is big enough?
At least like a billion.
At least like a billion. So a billion to the 10th is bigger than 3 times. So we could just try an explicit number, right? For instance. But I guess what this is less than or equal to what?
A lot of things.
I mean, I think we could look at that as the absolute value of 3, 3r to the 9th minus the absolute value of 6z cubed minus 3z squared plus 2z plus 10, right? And that would be equal. Now, okay, so we're going to choose an r sufficiently big that certainly, let's think through this, right? Like this has to be bigger than that, right? So we can drop the absolute values. Like right now we're trying to let's adding the condition that if this is bigger than that, we can drop the absolute values. So that gives us 3r to the 9th minus that. Now this here, we're subtracting what? We're subtracting this, right? So if I'm subtracting something, think about this. If I'm subtracting this business right here, right? And I'm trying to make this difference smaller. If I replace this modulus with something that's larger, we're subtracting something larger. So thankfully, we can just use the triangle inequality here. Yeah. The repeated triangle inequality. Namely, this gives me 6r cubed, plus 3r squared plus 2r plus 10. And so, can you guys tell me something that's kind of just intuitively clear to be less than this? 10?
Yeah, R equal to 10.
No, I want keep the r dependence here for a second. I think
Less than that.
yeah, I mean if r is big enough that this is larger than that, right? Then for that same r, this should be less than 2r to the 9th, shouldn't it?
Yeah.
Because this business here can't possibly be bigger than r to the 9th. So if I get rid of a whole copy of r to the 9th, this is smaller.
Yeah.
Now that we can solve, right? Because we've got 2r to the 9th less than r to the 10th.
And that's 2 divided less than R.
So unless I've made a dumb mistake, which is possible, I believe r larger than 2 should work. So we can say, I think r equals 2 should work. It should answer the question. I think all of the zeros of g of z are within the disk of radius 2. I think that's plausible for this function. What are you checking?
Their statement's correct.
Are you just looking, say, what are the zeros of z to the 10th? Or you can just plug in a Wolfram alpha, say zeros of x to the 10th plus 3x to the 9th plus 6x cubed minus 3x squared plus 2x plus 10, see what happens. Yeah?
Oh, but you're getting rid of a squared term. That's easy.
So this is number 5 on page 352 of the handout. We're supposed to show that there are 2 zeros in D1 and there are 5 zeros in D2.
Not correct.
Not correct?
No. Yeah, Z to the Z, like if about you'd have to choose a value bigger than 2. I set h of z
Let me just see.
equal to 2, and you get 1586, and then 2 to the 10th is 1024.
But
And you need that to be smaller, and it's not smaller for that to hold.
But you didn't just look at the original thing and find zeros?
Yeah, it was minus 0.9065, blah, blah, blah.
Okay. That's still within the disk radius too.
That's 1, 0. You said all zeros.
Yeah. If you find me a 0 which is not in there, then I'll believe it.
But that doesn't make sense. How does that hold and not hold?
I'm not convinced that that doesn't hold. I mean, these are complex numbers added together. There can be cancellations.
Yeah, but you have the real line in there too.
So you're saying if you just look at
The real line.
the real value,
Yeah.
but the only real value to look at in the circle is plus or minus 1. Well, plus or minus r.
Yeah. And 2 failed at 2.
This fails at 2?
Yeah.
So you're saying 3 times 2 to the 9th
Is bigger than 2 to the
plus this da-da-da is bigger than
Yes.
2 to the 10th?
Yes.
Huh, I wonder where we went wrong. Maybe it's in my assumption that this would be larger than that for, but that's probably here, that probably then, see, to go from here to here, we had to have that this is larger than that. So if that's not true for 2, then that would ruin my logic.
Yeah, I mean, and if you think about it, 3 times z to the 9th is less than is greater than z to the 10th.
Oh yes, very good. Good point, good point. So I would say, okay, so this doesn't work.
Yeah.
But this kind of gives you a suspicion that maybe we could just go, 3? I bet 3 would work then.
No, it wouldn't work either.
No?
3 times z to the 9th is equal to z to the 10th.
Ah. Fine, let's make it 10.
10 will not work.
10 will not work?
I think it might work, but I'm not sure.
Well, anyway, I have given you a path, but obviously we have to double check on my logical, like this is a very suspicious step right here, right?
Yeah.
If that doesn't hold for your choice of R, then
I understand how to do it.
yeah.
Okay. So you're just trying to like find something small enough.
Right. So I called it the perturbation. Like you need to. Well, there's two things to go on here, right? The one is to find something that is. Okay, so if we're within D1 of 0, so 2 zeros within D1 of 0. So I think we should look at it. G of z equals to z to the 5th plus 6z squared plus 2z plus 1. Maybe this. Oh, maybe this is the f of z. I mean, that would be, if that's f of z, that clearly has 2 zeros, right? And just 2 zeros. Because this has zeros outside. The zeros of this are on the circle of radius square to 6. So the number of zeros for f is equal to 2 for
So over here, when we take
D1 0. So in this case, we have to. So this would be my h of z, yeah. And what do we have to work with? This modulus of z equals to 1, right? So we'd like to show that if we use Gamelin's version of the theorem, we'd like to show that the modulus of h of z, right? We need to show that the modulus of h of z is what? Is modulus of f of z, right?
So do we do the same song again for E2? Like we just expand it out for Z10 and Z9? The first two terms?
Oh.
Example 2?
Example 2?
Yeah, like you just take f of z to be z to the 10th ends.
Oh, hey, that's a nice idea. So you're just like, instead of...
That makes it so much easier. Because then you can just...
Oh, yeah.
Straight up back to that like a cubic.
Very good. So your suggestion is if I could have let f of z equal like z to the 9th times z plus 3, which also clearly has, well, that starts to show you why you need z to, why you need radius bigger than 3, because that has zeros, it has 9 zeros at 0 and 1 0 at -3. So if the radius of our circle is larger than 3, then we can look at the perturbation as just being the third order stuff down here. And that's a little bit easier to sort through. That's a good idea for fixing that. Can you guys tell me why the modulus of h of z is less than f of z here? What are we looking at? We're looking at why is modulus of 2z plus 1 less than the modulus of what was f of z equal to? Z to the 5th plus 6z squared, yeah. Now, yeah, and we're dealing with what's the d1 of 0? The boundary is this guy, right?
Yeah.
So this.
So you get 3 and 6, or I mean, and 7. You just plug in, like if you just plug in the real number, because it has to be within the boundary. It's in the circle of 1. 1 is in the circle.
Oh.
1 plus 0i.
Yeah, but I need this. I need this for all.
Yeah.
Z such that modulus z is equal to 1. I need that.
Well, don't we know that power functions, like the way they're set up, they don't like collapse in unless they're under 1. So you're saying like if it's under 1, they'll collapse in.
I'm saying I don't know how to do it without thinking through it. Like I don't know right offhand. I mean this much we could. I mean. Maybe just a second here. So this is z plus 6, yeah? I mean, we could look at it like, we could simplify this directly like that, right?
Yeah.
But we're also working with modulus of z equal to 1.
Yeah.
So this is literally equal to modulus of z plus 6. So we need to establish that the modulus of 2z plus 1.
That's greater. That's greater than what we have right now. Because you said z to the 5 plus 6z to the 5. Which is greater than z to the 5 plus 6z squared.
I'm sorry?
Z to the 5 plus 6z to the 5th is greater than z to the 5th plus 6z squared.
Why?
The way you set it up.
This?
Yeah.
This is an equality. I mean, there's no. This is given
Wait, but how do you
modulus of z equals to 1.
Well, I'm asking how do you know the modulus? How do you know the modulus z to the 5th plus 6z to the 5th is smaller than z to the 5th plus 6z squared?
Oh, I'm sorry. You gotta tell me I made a typo here, which is misleading me. See that?
Yeah.
I got you now. I copied it down wrong. I made a problem too simple. Thank you. So that was a squared, which means I can't pull out that. I have to pull out z cubed plus 6 modulus of z. I can only pull out a square, right? That's your point. Okay, cool. Now I got you. Oh, I mean, the typo is the kind word. Stupid mistake would also be accurate. Let's see here, z6z squared, yeah. Now the question is, I shouldn't have I don't have this, I keep dummy. There, just 6, right?
Yeah.
Just 6. Okay, so why is 2z plus 1 less than modulus of z cubed plus 6? I mean, why is this true? We have some argument for that, yeah?
Yeah, I think you could argue that, like, if that, maybe, like, the max of 2z is
I don't know what that means, max of 2z. Z is a complex number. They're not ordered. We can't take the max.
no, I mean, like, but 2z is a function.
Yeah, but it doesn't have a max. 2z is complex valued. Max doesn't make sense for complex values.
But we're within the modulus of 1. We're within the
Yeah.
unit circle of 1. We're bounded.
Oh, So, let me think here.
Like, I think you can just look, like, I think you could make another problem that's analogous to this, saying the modulus of 2z is less than the modulus of z cubed. And I think you could just make that straight up and, like, look at that one. Like, I think that's a bit easier problem to look at.
I don't know, but we'll have to leave it here for today, unfortunately. So, why is this true? We need to show this. If we can show that, then we can apply Rouché's theorem. And that tells us then that the number of zeros of g of z in d1 of 0 is the number of zeros of f of z, which is clearly 2. But you're right. I mean, how do you show that? Yeah. This was number 5, wasn't it?
I'm not sure.
This is number 5 on page 352, which means we do have a alleged answer here. Well, they say, oh, interesting. They say use f of z equals minus 6z squared. See, we're not being creative enough. They used f of z is minus 6z squared. What? Anyway. Sorry.
I forgot to staple it.
Thank you.
I don't know where I turned them on.
Thank you, thank you.
Actually, I don't know where I turned them on.
Oh, goodness gracious.